Okay, we just talked about, or we have talked about how to find arc length for a function. Finite, the idea was to say, all right, I could get this arc length by maybe drawing 1, 2, 3 triangles, finding hypotenuse there, and hypotenuse there, and hypotenuse there. And that gets me a good estimate because it follows the curve kind. Yeah? But better is to do infinitely many Pythagorean theorem calculations so that it follows the curve perfectly. Yeah. Okay. So the idea starts off with the sum of many delta x squared plus delta y squared, or Pythagorean theorem calculations, but by the magic of an infinite Riemann sum, or the fundamental theorem, this becomes eventually the sum of many dx's squared plus dy squared. One of the big ideas, conceptual of calculus, is that when you take infinitely many, infinitely small, that delta y becomes this more theoretical microscopic change in y, microscopic change in infinitesimal circles. All right. After that, we had to do a little bit of algebra to get to the final function. If you remember, we factored out or divided out a dx squared, so that when you had a dx squared and you took out a dx squared, all you were left with is 1. Now we divided that dx squared out. So when you have this dy, when you divide out a dx squared, it's then dy over dx all squared. And then inside the root, the square root of dx squared is just dx. And so that's where we get our idea of the arc length, is this kind of quasi-Pythagorean theorem problem of lots of turning hypotenuse. Right? What's the plural of hypotenuse? Hypotenuse? Is that true? I'm just taking a guess. Is there a Latin student in the house? Can somebody actually tell me true? Is that hypotenuse? Hypotenuse? Oh, it's Greek. Oh, right. It's not Latin. Okay, I take your word for it. All right. Now, arc length in parametric is the idea of the day. And it is very much the same thing, but there are two small differences. First of all, what the path actually and the arc length actually indicates. And second, how do you deal with the t in there in the mix? So let's start from here. It's still the idea that we are dy squared and dx squared. But in parametric, the dependent variable is usually t. Sometimes it's theta, but mostly it's t. And that's going to change our algebra stuff. What do you reckon? Divide out a dt squared. So we're going to divide out, oops. Think of it like this. Divide out a dt squared. Now, what would have to go here then if I were to distribute back and it was to be back to dy squared? dy over dt, or dy dt, the derivative of the y function with respect to t squared, and x with respect to t squared. And so the arc length in parametric is the same idea, but cleaned up, looks different. It is more like the derivative of the y equation with respect to time and the derivative of the x equation with respect to time, integrating with respect to time. really pretty easy to use. Let's pause and just is yours correct? I don't know if I changed my notes. That needs to be y prime. Gosh darn it, I thought I fixed it. See that y? That should be y prime. Gosh darn it, in the box. It's not just y, it's y prime. Gotta fix that. Did you fix it? Yes. Okay, crucial. All right, so if I found the arc length of the path generated by x equals 3t plus 1 and y equals 9 minus 4, 2t, we could graph the path, but it doesn't say, so let's just find the arc length. The arc length then is from, now you can see that the limits are not x limits, they're t limits, they're prime limits. And x prime, what is it? 3, which needs to be squared. And y prime, what is it? -4, which needs to be squared. So the arc length then is 0 to 2 of what? Just basically the square root of 25. So what's the antiderivative? 5. And so arc length is 10. Now, arc length in parametric actually has a second layer of meaning. When you find arc length in parametric, you're finding the length of the graph. But in parametric, isn't the graph the actual path of movement? So when you're finding arc length in parametric, you're finding distance traveled in 2 dimensions. And that's not the case for one-dimensional or linear movement. Planar movement we'll talk about on the back. You just found the distance traveled. This represents the distance in 2 dimensions in a plane traveled. Two L's or one? Is it one? Is anybody really good speller? Is that 2 L's or one?
One.
One, you think?
It's weird, so it's one.
It does look weird.
That's how I do grammar, and it works.
No, it definitely.
I'm a pretty good speller, right? I'll have to look that up. All right. Now, in terms of on a calculator and what I expect to see on a calculator, this is called the Lissajous curve. There's a whole famous families of curves. Gosh, there's centroids and all this great stuff we're about to talk about. But this here curve has a parametric family. You can see that x gets bigger and smaller, and y gets bigger and smaller, but at totally different rates or different stretches. And that represents then, or gets shown in this kind of crazy curve. Now, if I asked you to find the length of the path with calculator, give that a go, please. Try that with your calculator, and then I'll reveal the box as far as what I want to see.
Oops. Remind me to give me your my calculator. What if I don't want it?
So I'm so glad you asked that question. I'll come back to it.
Wait, there's an answer like this?
Yeah, no, that's very much my next point I might want to make. It's like you're reading my mind.
That's exactly what's going on.
Great minds think alike, eh?
Yeah.
All right.
I'm just trying, guys. Don't ask me. Oh, it's squared, so I don't have to worry about science.
Physics students, make sure your calculators are reading.
I don't use this calculator.
Oh man, I thought it was good. That's smart. It's a good thing it probably doesn't work. Let's try. Because I've started Christmas before. That's how you read it, remember? doesn't work. It's very angry. It's very, very angry. Don't do that.
So, my dad has this friend, and he does things like that. So,
Okay, are you ready?
No, no. Guys, what's the thingies? Don't.
Are you getting something like 58.678?
yeah.
Okay, now in terms of the work here, this is actually on the back. I didn't want to give you the answer, but if you flip it over the paper, not your calculator, that's so stupid. Okay, if you flip it over, this is the work I would like you to show on a calculator active problem. If the equations aren't so filthy that you can do the derivatives, then I would like to see the derivatives. Okay, so this is my preference. You see, this is showing the derivatives in there. You with me?
Yes.
Okay. If the equations are so ridiculously gross, some huge combination of functions that you just don't want to take the derivative of, then I would take this, where you're basically just saying, hey, calculator, give me numerical estimates of the derivative of x and y in there, and that would be okay too, especially if you have the functions in there. But my preference is, if possible, show a calculator derivative, yeah? If you had this, if you wanted to do this graph the proper way, you should be showing both original position and direction of movement. How do you do that?
Find where t is 0,
Yeah, so when t equals 0, what is the initial position?
x is 1.
X is 1 times 4, so 4, and y is 0. So here's your initial position. And I guess if I had these in my calculator, I could hit trace and just see how the cursor moves. Yeah, that's one way to see the direction of movement. But in terms of calculator, or sorry, calculus, how can I use calculus to find if at that point it's going to go up or down?
X is
Plug in another
y,
So would I take the derivative of x or y?
y.
Why?
Okay, you would take the derivative of y, because at that point x is neither changing, it's at that instant x it's not changing at all, but at that instant y is going to change. Yeah. So take the derivative on y. What is the derivative with respect to t on y?
Positive.
7 cosine t at 0 is positive, and so that direction must be moving up. It's going like this, and then it comes back this way. Obviously, you can say clockwise or counterclockwise because it's all over the place, but it goes that way to its path. Okay? Are you with me? Okay. Let's pause. It's been probably a long day for you, so we need to get you up and exercise. So this is what I'd like you to do. Take your phone, and
I have it.
you're going to, or you and your partner can do this or whatever, but you're going to go outside from my room and go to the middle of the hall, yeah? All right. Now, I want you to start your timer, start when it's your turn and you're at the very start of the first diamond in the halls. I want you to walk this way, which is basically how I walk down the hall every time I walk down the hall, until you get to the end, and then at that point, stop your time. Time end is blank, all right? Are you with me?
Yes.
I want you to, from the starting point, I want you to go right, not left. All right. Furthermore, from experience, I've taught this a lot of years, when you come back, please don't walk through the middle. Why not? Oh, no, the rest of you are still doing it. Okay, so walk around the outside so not to mess up somebody else. So you're going to walk to the end, stop your time, and walk on the outsides back to my room. Understood?
Yes.
Okay, be extra quiet when you pass Miss Hannah's room. Again, from experience. Yeah. Okay?
man in the back.
You are quick. What time?
I don't have one, so I just did it for fun.
You just counted?
No.
You didn't even count? You didn't do somebody else's count?
Mm-hmm.
Other than that,
I walked down the middle. I walked it down the middle. 42.
What?
Neat. I walked it down the middle. I wanted to pass to the love the snail. I'll just 42.
I really, like, I thought I was like, I shouldn't say it, and then I said it, and I was like, oh, I just went there. Yes. No.
Okay, do you have a time?
Yes.
Yeah,
40.7.
All right, so the objective, I gave you some scratch. This might actually be on the back of the parametric notes. I can't remember.
Yeah, they are.
They are? So if you have your parametric notes, you might be able to put this on the back of your parametric notes. Otherwise, use the, when I say parametric notes, I mean set 106? 7? Not the original parametric equation. Are these in order? Okay.
What lesson number? It's lesson parametric.
Yeah. Okay, so if you have your notes in Sarah 106, cool. Otherwise, just use this. It's just to accumulate. But the idea is, the beauty of parametric equations is it allows you to take real life movement and put it into predictable math equations that model that movement. So you're going to do what's called modeling. You're going to model the movement based on your data. Now this is, I will give you a little bit of guidance. First of all, there are 11 diamonds. Okay? Now, truth be told, if this had to be perfect accurate, like space shuttle accurate, then there's double diamonds, and that makes double squares to middles, and that makes things a little more complicated. But we're going to do a little stripped down, simplified version. Each one is 5 wide and in each direction, and or 10 across and 10 vertically. All right. So let's start here. I'm going to say we're going to all call the point at the very first diamond in the middle as the order. Okay, we're going to use that as a reference. So that is 0, 0. You follow me? And you all started at time 0 there. So that's a point. Now, the modeling process then gets to say, okay, I need more data. I need to figure out, all right, where else was I? Let's go to the end. Your time at the end will probably be different than everybody else's. But the x and the y should be the same. Now, if we look at both x and y in reference to this axis, then where did you end x-wise? 0. You're back to the middle, okay? X represents side to side, and you end at the middle. What about y? Given that the diamonds are each 10 square, they're foot square tiles. 10, but there are 11. There are 110 total square tiles you walked going that way, yeah? And then the time is whatever your time is, right? Now, we need to fill in the gaps in between. So I would suggest the third point you find is this one. Time is blank, x is blank, and y is blank. What's x? Actually, let's start time. How will you find that time? Assuming uniform motion. Now that's actually a huge assumption. Yeah, time divided by 11 is when you were there. Your time end divided by 11. And again, we're going with some assumptions, and that assumption we just made is that you're using uniform motion. Which is impossible. Not very likely, but we'll go. Okay? Would be great. Really great problem. That's right. Anyway, what's x there? 0 and y is? 5. 5. No, 10, you're right. I'm an idiot. I was thinking already the corner. Okay. Now, your next point of interest would be here. Time, x, and y. What's your time?
Divided by 22.
Divided by 22. Time n divided by 22. What's the x?
5.
5 and the y? 5. Okay? All right. You might need a few more points, but that should get you started. Now, the goal is this. Within maybe, I'm hoping maybe 5 minutes, I want you to tell me this is the equation for where I am horizontally at any time. This is my equation for where I am vertically at any time. Go.
Y is a line.
Somebody, how long did you take? 40 what? 45? That's cool. I'm going to say 44. My time was 44. Haha. Love it. That means I put 4 there, and 2 there. And only I can fudge my results. That's not something you have to do. Your side. I'm a math person. Perfect measurement is possible. No.
I know, I was sitting here.
Just move it. You're gonna move it back, right?
I mean, he's not the only one.
Maybe we should we all go with? I don't want to fudge the results, but maybe it would be easier to check our work if we all went at the same time. Yeah.
420.
Yeah.
Okay. Let's go with 44.
420.
Use 44 seconds for the time. Okay. It'll go beautifully.
You don't want to know the actual equation, do you?
I want x and y equations as a
Oh,
function.
no, not you.
Oh, okay.
And if you do, you can always solve it in your free time. I don't want to solve this in your free time. Your free time usually I've got nothing better to do at midnight. Except write college essays. Nope. I'm showing you an application number 8. Not all of them. Really, most of them. But if you look it up, some of them give you an extra 10 days, which I am no party to. Yeah, it's really pretty. There's a lot of yeah, everything is like really old. Their buildings are older than the country.
Yeah, I know next upstairs, then this, so then she got stuck in the back.
It was magic. Magic vacuum changes jewelry. You put an earring in, it becomes a necklace.
Like, for the metal.
I feel it's just like a bunch of
You take your data and graph it. That will get you the easiest way out. You draw a picture of your data and your relationships, time against x, time against y. It's much easier to look at a picture of the data than just the data raw.
yeah. Y is ratio is 2.
I'm gonna do this.
Like on a scale of 1 to 10, how would that go?
Why is a line? That's fantastic. Wait, so how do you think it again?
It's like 2 pi over. I don't know, actually I did that wrong. No, I didn't.
I rate's pretty good.
Now are you ready? If you get your equations early, feel free to go to the calculator and put them in and see if it works.
I needed to get to variance. I don't know, we don't have to be the same. Now there's a chance that one of us gets this right.
Oh. Switch between negative.
Mathematics is cheap.
Ready?
I did it.
What is your x equation? 5 sine of what t? Pi over 4t, yes. 2 pi divided by the period of the graph is the coefficient,
Well, I
right?
just didn't label my graph right.
Okay, what about a y?
5 over 2t.
5 over 2t. For what domain? For time from when to when?
From 10 equals 0 to 10 equals 40.
0 to 44. All right, let's check it in our calculator, practice putting this in our calculator, see if we did well. So, we obviously don't want to graph in function mode, so how do I switch gears and go to?
You hit your calculator hard.
Go to menu, and I go to
You go to parametric.
graph entry, and we want to change to parametric, right? X is 5, we said sine. Oh, shucks. What's happening? Well, it's so small on me all of a sudden. 5 sine of I t 4. Was it 2/5 or 5/2 t? I can't remember. 5/2. T. Obviously, we're going to need to change our window. Okay? First, we need to change our domain. Right now, how much is time going to go through? 6.28 or 2 pi. We need to go through more, so you're going to need to change that to 44. And do I have a space there? Okay, great. Now we need to change our window to see more. Go to window, settings, X. We are technically only going -5 to 5, but I'll go -10 to 10, so it's not going all the way to the edge. What about the Y's? What do we need to go from and to? 0 to 1, 10. Okay. Scale by maybe, I don't know, 10. I don't know. Okay. Boom. If you hit trace along.
Well, mine didn't go all the way.
There I go. Whee! I'm going so fast down the hall. Miss Hannah's going to kill me. Aha. All right. So, I hit trace. And boom. All right. Now, all that's cool. Let's go one last supplemental problem. Say you didn't go around the outsides of the hall coming back. Say you came back down the hall the same way. What are the equations now? No. Equations for there and back. No. I don't mean what's the equation for back. I mean what is the equation for there and back.
So it would be the
Why is now giant?
Is it absolute value?
Absolute value.
So you create a sine. Make everything triangles. And then round the corner. Make it sidey, so.
I definitely did not.
How are you gonna do it? The x, will it change, or will the x still be good? X is good, the y needs to change. Try something and verify it works or doesn't work.
I'm pretty sure that works. I know you said. Wait a minute, I think I actually did do it right. Because it goes.
He wants a sign.
No, I did it wrong.
No, maybe this.
Also works. We just really slow down.
Was it 110?
He's using signs to practice. I know.
Yeah, but then it's not safe. That's so he's saying too much. It's like saying, I'm going about 40 miles an hour when you're going 60.
Graphs don't lie.
Okay, anybody have it yet? -5 halves, absolute value.
T minus 44 plus 110.
Plus 110.
Yeah.
Let's verify. At time 0, does it do what it should do? At time 0, I get -44 times, that would be 2 goes into 44 is 22 times 5 is 110. -110 plus 110 checks at time 0. Good deal. At time 44, we should get 110, yes? And we do. It's definitely working there. Like it. At time 88, what should it be back to, assuming uniform movement? 0. This is 44. 88 minus 44 is 44. 5 halves of 44 is the same as we already talked about. So boom, well done. That you guys? Good job. Well done. Okay, so that would be coming back. Alrighty. I talked about this a little. I think I'm going to touch on this tomorrow. Let's do a couple off the homework if we can really quick.
Let's just do the whole set.
Do the whole set. Anybody have their book open already? Number 14. Just my technology.
It's okay, we don't have to do number 9. I can figure that out.
114. Sorry, number.
We're so close
Sorry, I
to
should
the
have done this already. Okay, so would you talk about number?
140.
Let's see.
After that.
4.
Yeah.
And oh wait, no, 4 is just gravity, isn't it? Oh, 6. Excuse me, 6. 6. X equals 2 cosine of theta. Y equals.
You don't have a number 6.
You don't have 6?
No, it's number 8. You might made your own.
Oh, I made a super problem?
Yes,
here.
pretty
Oh,
sure.
my bad. Do I have time to get through all that big boy?
Probably not.
No,
So just write it now and finish it tomorrow.
If we skip, if we skip today, just like half.
This is calculator active on that 8, number 8. That's the AP response. Let's just say it's not good enough. Okay. All right. Sorry, I blew it. Have a nice day, though. Lovely to see you. Nice to have you back. We will get through some 148.
Did you enjoy your butterflies?
Ah, actually, before well, I put it in my bag last week, but then I forgot it was there. So it kind of exploded in my bag 2 days later. But I kind of scraped it off the sides of my bag, still put it in the oven. Pretty good.
I need to put my thinking straight.
Now it's time.
It's right here. Because I'm reading too many stuff together and it's like, bright red paper. Yes! Mr. Rickman, can we have bright red paper? One of our lessons needs to be a bright red paper.
Well, why would I do that?
So then I have more paper on my binder.
They're my chapters if I would need to like invent a new chapter of calculus.
No. Some of them are double. Like, just do it
Oh,
for us.
instead of going double green, I could go a bright red.
Yeah.
Oh, stop bright red. It would be a special
And
word.
instead of going gold, actually go gold.
Gold,
Like real gold.
Goldenrod?
Yeah, just use real gold, Mr. Rickman.
Sure.
I'm gonna take a missing assignment.
No, that would be on the lesson.
Yeah.
Anyway.
Oh.
Coats would be priceless.
Oh no, they'd be pricey. Hold on, Micaiah.
I never understood the word priceless. Like, why do they call something priceless that actually has a lot of price?
Well, there are things that are like priceless, like you cannot actually put a value on.
Yeah.
Like my dog. I wouldn't
Priceless.
sell it. He's priceless. He's amazing. Like, Caddy, I wanted your dog. Well, that sucks. He's mine.
It's good to be back.
Ben, you're in this class. It's so weird.
Yeah.
Your choice. Choose your pod.
Yeah.
It's not like it's in stone. As long as I can make a seating chart by the end of the week, that would be great. Doobie-doo. I need to space
Didn't work
that out.
thing. Parametric.
It's me. Hi, B. This is the pod. Actually, my desk job this is supposed to be. Look out.
Yeah, it might be gone.
It's not
It's
bad.
Supposed to be. Oh, hey, right. It kind of depends on how well organized your notes are. If you have really organized notes, then you probably don't. What's this? This goes to a good place. What are you doing, Jack? You're trying to help. What are you doing? Oh, no. This is this is supposed to be good sight lines for that. So it's weird. Whatever. These are sites. Alrighty. Alright, how are you?
I wish I could do the calculus. Instead I had to like play Pia by the end to grab it and do the calculus.
I'll explain. You might need to answer your question. Shooby-doo. All right. Hi, so many smart people. Drew's here.
Yeah, pretty much.
Hey, all right, hi, welcome. By the end of the week, try to find your place, be welcoming into your pots and hey, hi. I don't care if you move desks around a little, as long as I want to move them back after. All right. So, hi. How are you? That's, yeah. Wow, so seniors are 12 of 12, am I right? No, apparently not. Oh, yeah. I just started your 12th semester, you're almost done. Hard one, it's like the home stretch. That's your usual. All right. Well then, good stuff. Let's get you going. Will you go to box 3 and try 3, please? And then 22, do a little warm-up. Let's see how rusty you are. There you go. Not very rusty.
It's the diagram. He talked about all of you still have it? He prides himself. How did he pride himself? No, it's really he's like. No.
It says calculator and then no calculator.
Let's use these directions up here.
Yeah, I know.
And then once the seniors started back to school, they're fucking
This class seems a little rustier than
no, the senior girls.
You didn't learn our place?
No. Did we learn that? Oh, it's all the natural law of
The integral of secant or the antiderivative of secant is log of secant plus tangent. Yeah.
Very good.
The absolute value.
Isn't this semester basically going to be like a bunch of series?
Series, lots of series, baby. You're gonna love it. Totally different math than you've ever experienced. Okay, so I need tickets for 8. 19, I'm missing something. Let's see. Gary? Where's Gary?
He's probably flying back from China.
Really? You went to China?
Yeah.
Wow,
Like Shanghai or something.
cool. All right, Gary's absent.